people mostly cleared out of the commons? You ready? Okay. Hello, everyone. Welcome to Scientific Python. This lecture is going to focus mostly on NumPy and pandas. We'll also be using a little bit of matplotlib to do some visualization, and we'll look just a tiny bit at some actual neuroscience data using Babel, but mostly we'll be focusing on NumPy and pandas. Just a quick disclaimer, if you realize 10 or 30 minutes into this lecture that you're in the wrong lecture and you really ought to be in the intro or the design of libraries lecture, you should feel free to just go. I'm not going to be offended if you walk out of my lecture because you're in the wrong place. Yeah. Oh, yeah. Sure. How's that? I'll do my best not to knock this over or anything. Okay. Right. So feel free to, if you realize you're in the wrong lecture and you'd rather be in the design lecture or the intro lecture, no problem. We understand. Okay. So in this lecture, I'm actually going to do everything just live coding. So if we start out, go ahead and open up your Jupyter notebooks, and we'll just kind of work through all of this this lesson together. If to start out, I've just got the schedule and Zoom links open here in my Jupyter Hub, and I'm going to close those. And then I'm going to go to the curriculum directory. And then if you look in the curriculum, there is a Benson Scientific Python directory. And you can go ahead and go in there. And you'll notice, I'm not actually going to use these today, but you'll notice that there are two notebooks in here. And they contain all the material I'm going to try to go through with a lot of comments and notes and things. The idea is that these are not what we're going to use right now, but they are there for you to review later if you want to review anything we're going over today with additional explanation. Now that said, what I'm actually going to do is I'm just going to start by launching a new empty Python 3 notebook. And I would encourage you to do the same. If you want to have these open in the background in case you get lost or something, that's totally up to you. But I'll just be kind of walking through in live coding, and my hope is that you'll just kind of live code along with me as we go. I also just want to say that there's nothing in this lecture that's so important that you shouldn't interrupt me with questions. So please do interrupt. This is intended to be a little bit informal and to focus on things you're interested in. And if we have extra time at the end, which we may, I'll just poll the audience for what you'd like to hear about, and we'll talk about it. Okay, but we're going to start out with NumPy, because NumPy is really the kind of foundation of almost all the scientific libraries in Python. So NumPy fundamentally is it's a library that handles pretty much all of the numeric utilities you would need in Python, as well as arrays. And arrays are the really big, the main kind of focus of NumPy. So I'm kind of assuming that most of you already know, are fairly familiar with Python. You don't need to be experts by any means, but I'm kind of assuming that you already know what like a list and a tuple are, some basic things like that. You know the difference between an integer and a floating point number. So I'm going to kind of assume that you have that basic level. But if you have questions, please let me know. Just stop me. However, to start out with, we're just going to go ahead and we're going to go ahead and import NumPy as NP. Is this big enough everyone can see it okay? Should I make this? I'm actually going to make this a little bigger, and then I'm going to click this little folder here to hide my folder view. So hopefully that's easier to read. Okay, everyone can read that then, right? All right, so NumPy, people, when they import NumPy, they pretty much always import it as NP. That's pretty standard, and it's, yeah.
Getting to the Jupyter Hub.
Oh, is that a problem anyone else is having? So if you go to neurohackademy.2i2c.cloud, it says
starting up, just wait.
Oh, okay. That will probably resolve itself in a few minutes. Unfortunately, sometimes when everyone starts up a server at the same time, it takes a little while for some people. If it's still not working in a few minutes, try refreshing it, and we can worry about it then. Unfortunately, there's probably not going to be a lot I can do if it doesn't start right now. But But I'll go kind of slow at the beginning. Okay, so pretty much everyone who imports NumPy always imports it as NP. That is just the kind of common name, the conventional name for that people use for NumPy. And so we'll go ahead and import it just like that. And let's just start by making a simple array. Almost everything involving NumPy is built around the concept of arrays. So we'll just say u equals np.array. And then we're going to pass it a list to initialize the array from. And I'm just going to make this a really simple 1, 2, 5, 7, 1, 3, 5, 7, excuse me. If you need to start a new file, there should be a big plus button. Yeah, and then you can click the IPython kernel button. Yeah. Okay, and then I'm going to put u here because this returns the array and captures it, but won't print it out. But I'm going to actually display the array at the end of the cell here. So, not surprisingly, it says we have an array containing these numbers. So, if you've never seen a NumPy array before, and actually, let me just get a quick show of hands. And if you're online, you can use the reactions button to raise your hand for this. But if you have, would you raise your hand if you have, if you're at least passingly familiar with NumPy, if you're basically here for a review? Okay, okay, great. And how about if you're new to NumPy and you're here to learn it for the first time? No judgment. That's kind of what we're here for. Okay, great. Good to know. All right, so initially what we've just created is an array that contains the same things as this list. So we might be wondering, how is this actually different than a list? Or is it different than a list? And the answer is yes, it is different than a list. It's quite a bit different. Sorry, the microphone just died, I think. I'm not sure I have batteries, so I'm just going to try to talk loudly if that's okay. If you can't hear, just raise your hand. I'll do my best. Okay, so let's think about this a little bit. If we have this list 1, 3, 5, 7, one of the things you can do with lists is you can set an element. So if I wanted to make this 3 into something else, I could say L of 1 equals 11. And that's fine. And you can do the same thing with arrays. So if I want to set u of 1 to 11, that works just fine too. Keeps it as an array. Now, however, if I want to set the list's second element to be a string, for example, that's totally fine. Lists can contain whatever kinds of data you want, and the elements don't need to be the same. With arrays, however, arrays are optimized at a very low level in memory to be very efficient at storing things. And so if you try to set the same elements of our array to a string, it's going to give us an error because we made an array of integers and a string is not an integer. And so it doesn't know how to fit that string into the memory where that 11 would go. So one of the differences between arrays and lists or arrays and tuples is that arrays have to have all the same kind of data. A lot of the things about arrays and lists are very similar, though. So we access them in the same way. So if we want to access the first element of u, we just access it the same way we would with a string, or excuse me, a string or a list or whatever else. We use the open bracket syntax. Now, that isn't to say that arrays and lists are accessed the same way. There actually are some really important differences. So for example, if I wanted to extract just the first and the last element of a list, I can certainly extract the first element, and I can extract the last element. But if I wanted to get them both in a list, I would need to do something like this, where I made a new list containing those two elements. On the other hand, with an array, I can actually pass it a list of indices. So I can say 0, -1, requesting the first and the last elements, and it will give me back an array with just the elements I requested. So this is one difference. This wouldn't work with a list. If we do this with a list, it thinks we're looking for, it thinks this is like an integer or something, and it's going to raise an error. Indices must be integers, not lists. Okay. Arrays. So with lists, if you wanted to represent a matrix as a list, we might say something like the identity matrix might be represented like this, where we had a list of lists. We had a row for a list for the first row and a list for the second row. We can do that with arrays as well. And in fact, arrays are made to store not just vectors, but matrices and higher order tensors with lots of dimensions. So let's just make an example array. We'll make a matrix. And I'm going to initialize it from a list of lists like this, but it will then become an array. So I'm just going to make up some numbers. It's not important if you use the same numbers, really. But we'll make this, we'll initialize it with a list containing 3 lists, each of which have 2 elements in them. So, and this time I'm using floating point numbers. And then I'll put M here just we can see the output. Okay, so this made an array that has 2 dimensions. It has rows and columns. And it basically matches the organization of the list that I passed in. Now, how many of you are coming from either MATLAB or Julia or R as your main languages? Yeah, okay. MATLAB is still very popular in neuroscience and probably will be for a long time. R is getting more popular, and Julia, I wish were more popular, but it's not. If you're used to one of those languages, you're used to a column-based language. Now whether a language is column-based or row-based doesn't actually matter for most of our purposes in this lesson. I just want to explain it very quickly. Basically, conceptually, in Python, a matrix is a column of row vectors. In MATLAB, a matrix is more like a row of column vectors. That really, now that comparison only goes so far because we index things the same way in both languages. So whether you're in MATLAB or Python, if you want the second row and the first column, you're going to put the row first. So the second row is row 1, and the first column is column 0. You're going to put the row first and the column second. And that's true in MATLAB or Julia or R or Python. Like we always index row, then column. And you'll see that pulls out the 0 here because it pulls out the second row in the first column. When I say row-based or column-based, really what I'm talking about is how the matrix gets stored in memory. So in MATLAB, you store the columns in like contiguous pieces of memory. In Python, you store the rows in contiguous pieces of memory. That's all I'll say about that for now. If people have questions about this, I'm happy to talk about it a little more. But this mostly comes up in like high performance computing, where you need to really think about where your memory is or where things are in memory. Regardless, that's something you may have heard of. Python is row-based. Also, in case anyone needs a review of this, Python is 0-based. So the first element of any array or list or tuple or anything is element 0. The next one is element 1. The next is element 2, etc. So just in case you're used to MATLAB, Python is not a 1-based language. We can also, in addition to arrays like the array U we made and matrices like the array M we made, we can also have arrays that are just single numbers. So if I say X is array 12.7, not a list, just the number 12.7, that's totally fine. That creates an array that just contains 12.7. Really, you can kind of think of the array class as being almost like a tensor class in terms of the mathematics of it. Tensors are just a name for arbitrarily dimensioned arrays, basically. So a vector is a 1-dimensional tensor, and a matrix is a 2-dimensional tensor, and like an MRI image, which has 3 dimensions, spatial dimensions, is a 3-dimensional tensor. A number is just a 0-dimensional tensor. So that's why that works. Okay. let's go back to our matrix just for a second, the matrix M we created. You're probably familiar from lists that you can use the slice operator. So you can say, for example, I want the second element, element 1, to up until the end. And you can put just 1 colon, and that says starting at element 1, which is the second element, all the way through the end of the list. And I think I've got that in a markdown cell. Yeah, okay. If we just evaluate this by itself, we're going to get 2 rows of our matrix. And that's because what we're asking for is the row 1, which is the second row, up to the end. Now, if you're used to MATLAB or Julia, when you only provide 1 index, you're indexing in a different way than in Python. So let me just unpack this a little bit, because this is a common source of confusion. In MATLAB, if you have an array M and it's got 2 dimensions, and you say M34, you're asking for the third row in the 4th column. But if you ask for M12, you're asking for it to turn that matrix into just a vector and then give you the 12th element out of the vector, which is a different way of indexing. Same in Julia. In Python, that's not how it works. In Python, that's always just the row index. So if we ask for M12, it's going to say, well, let's ask for a smaller number, M6, or 4. It's going to say, yeah, there's no 4th row in your matrix. So it doesn't work. If you wanted to just get the 4th element, you could say m.flat and then ask for the 4th element, or the 5th element, I should say. Any questions on that? Okay, great. So we can provide just some of the indices, just the first, like the initial indices for a matrix, without providing all of the other indices. And so, for example, if we wanted to get all of the rows but just the second column of our matrix, we could put an empty, excuse me, a colon here just for the generic slice operator, and then we could put 1, meaning we want the second column, and that'll give us back a column vector. I mean, it's just a vector. It's not, there's nothing about this that's actually column versus row. It's a one-dimensional vector. In MATLAB, it would actually give you back a column vector, and that's a little different. But in NumPy, vectors are just one-dimensional tensors. They don't have a hidden other dimension, a hidden rows dimension or a hidden columns dimension. Similarly, if we ask for the first row 1, the second row, and then all columns, we'll get back one of the rows, which is exactly the same as just asking for M1 without this slice operator. Okay. So before we go too much farther here, I'm going to say let's actually look at some real data, some real neuroimaging data. So you're probably all aware that one of the most common places we encounter arrays as neuroscientists is if you do any kind of MRI. Every MRI image you take comes back out of the scanner as a 3D array, where you've got rows, columns, and slices, or X, Y, and Z, or whatever, what have you. You've got 3 spatial dimensions. So we're going to actually quickly use this little library called CloudPathLib to load in some data from the natural scenes dataset. Now, we're going to talk a little bit more about CloudPathLib tomorrow morning for the week 1 projects. But for now, just follow along with me and I'll kind of explain what we're doing. So we're going to say from CloudPathLib, import CloudPath and S3 client. We're going to load some data off of Amazon's S3 storage using this library. So we need to import both CloudPath and S3 client. We're going to go ahead and from OS import FSPath, and I'll explain what that's for in a second. And then we'll import NeBabel as nib. So if you haven't used it before, NeBabel is a library in Python that knows how to read and write all of the standard neuroimaging file formats like Nifty and all the FreeSurfer file formats and stuff like that. So we'll be using that to decode the data we load from the NSD.
Import error from CloudPathLib import. info error says cannot import name S2 client.
S3
Oh,
client.
S.
Yeah. Okay, we're gonna say client equals S3 clients. Whoops. And we have to, we're just gonna create an S3 client object, but we have to pass one argument, which is no_sign_request. This is basically because S3 usually requires you to authenticate, but this is a bucket that's public, and so we want to say, don't authenticate with this bucket, basically. Then we're going to say NSD root equals cloud path. We're going to provide it the string s3 / natural scenes dataset. That is the address or the ID for the natural scenes dataset bucket. And then we just need to provide this client as a second argument to that object. Okay, hopefully if you run that, it'll work. I'll make sure it stays on the screen for a minute. So what this does is it basically establishes a connection to this Amazon S3 bucket. And this NSD root acts as sort of like a representation of that directory and its contents up on Amazon S3. So if you've ever used the pathlib library and the path type in Python, which is for browsing your local files and directories, CloudPath is exactly the same, pretty much. It has almost the exact same interface. It just works on S3 and Google Storage and online repositories and such. So again, if you're not sure how well this is working, don't worry too much about it. We'll talk more about it tomorrow morning. And we just kind of want to get some data loaded in here. So what I'm going to say next is the anatomical directory path is equal to the NSD root / NSD data_raw data /sub-01 /session NSD anat /anat. So there's several subdirectories we need to go into because the NSD is organized into nested kind of subdirectories. I'm going to have anat dir path printed out at the end here. And if you want to check if this worked, so even if you have a typo in here, it's going to be fine with it because paths don't have to exist. You might be making a path that you're going to create or something like that. So if you want to check if that you got all the typing right and everything's working, you can ask if this is a directory. This anat dir path is a directory, and it should say true. And if it says false or it raises an exception, then there's probably you have a typo somewhere in here. Okay. Any questions so far? Am I lost anyone? All right. Okay, we're going to do just a couple more things here. What we're gonna do is we're gonna load in a T1 weighted image from the first subject in the natural scenes data set. This is just their anatomical T1 scan. So we're gonna say T1 file path is equal to the anatomical directory path / now, if you're familiar with the brain imaging data structure BIDS, this file name will look really familiar to you, and if not, you'll probably think it's very long and verbose, but this is how we do it. Sub 01 _ ses per session NSD anat _run 01 _T1 weighted.nai.gz. And I'll just say, yes, that should be NSD anat. Thank you. That probably would have taken quite a while to figure out. And I'm just going to check that this is a file that it knows about on S3. Assuming that worked for you, then you should be able to say image equals nebabel.nib for nebabel.load. And then we can't just pass in the T1 file path because that's it's an S3 path. It doesn't actually exist on the local computer. But if we call that FS path that we imported from the OS module, it will basically say, hey, T1 file path, give me a local path on this computer, and the T1 file path will go and download the file we need and give back a temporary directory or a temporary file that it can load. So we can just say nebabble.load fspath of t1 file path, and then I'm going to have image printed out at the end. Now this ought to take, oh, that was pretty quick. This ought to take just a few seconds to load because it actually needs to go download that data for you. That said, we're running this Jupyter Hub in the Amazon cloud, and it's on Amazon S3, so it should be pretty quick. Okay. Did anyone get an error when trying to do that? What do we got? So if you think you just made a typo, you can always go over to the Intro to NumPy notebook, and if you scroll down a little ways, you'll find this set of code that we're going through. But I'll scroll up here so everyone can see and make sure they got things typed right.
What's NIB?
NIB is the NeBabble library. So up earlier we said import NeBabble as NIB. Yes. Yep. Yeah.
Should our, what's it called, like the location and hexadecimal at 0x, blah, 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 should that be the same as yours? Or
No. No, that's I believe that's telling you something about where in memory it's located.
Oh, okay.
So I don't think that matters. Yeah. Oh. Okay, anyone having trouble getting the file loaded? Okay, awesome. So when we had it print out the image here, you notice it didn't print a NumPy array. It printed what's called a nifty1 image. If you don't work with MRI as much as I do, nifty is just the kind of universal standard file format for sharing MR images. And it contains a little bit of metadata in addition to the voxels that tell you things like how the brain was oriented in the scanner and which direction is forward and right and left and things like that, and the size of the voxels, et cetera. But there is a field of this object called data obj, which basically contains a NumPy array. Now, it's not actually a NumPy array. It's something very similar to a NumPy array. And the only reason for that is because MR images can be really big, and you don't want to load the whole thing in. You just want to load in a little bit of it. So this is a special kind of like pretend NumPy object that only loads the data when you ask for it. So to make it into an actual NumPy object, we're going to say array equals np.array. Whoops. And just force this image.data object to become an actual array. And then I'm going to have array print at the bottom here. And when I run that, it should print out a bunch of numbers. Now, these numbers should be the same, assuming you loaded in the same subject's T1 image. Okay, so we've got this array here, and you notice that there's 3 nested open brackets here, which indicates that we've got lists of lists of lists or something like that in our array, which means we've got 3D data. Okay, so let's query this data a little bit. First of all, you notice there's a bunch of ellipses in here, basically saying I'm not going to print this whole array, it's too big. So it'd be nice if we could tell what the dimensions of the array actually are. And we can do that with the array.shape field. So every NumPy array has a shape. And the shape is just rows, columns, slices. If we look at a different, like the matrix we made earlier, m.shape is just going to be rows and columns because we only made a matrix. Similarly, u.shape, the vector we made earlier, is just going to be 4 because it's only got 1 dimension. And if we remember that x we made, which was just a single value, oops, its shape is just an empty tuple because it's a single number and it doesn't have any dimensions. You can also actually request the shape of something that's not an array using the np.shape function. So now, usually you just if you had a list and you wanted to look at it as an array, you just turn it into an array. But if you have something like this, list of lists, it'll basically say, well, if this were an array, what would its shape be? And for in this case, it's 2 by 2.
Non-numeric, but does it have to be a numeric? thing?
Yeah, great question. Does this work for non-numeric arrays? And the answer is yes. Actually, NumPy works just fine with non-numeric data. So you can, for example, have an array with a string in it like this. Now, if I make an integer array and I try to put a string into it, it's going to say I can't fit a string into an integer. But since I'm making this array with an integer and a string, it's going to go, oh, this, I don't know, I can't put strings and integers into an integer array, but I can put them into an array of Python objects. And so it makes a special kind of object or array that well, okay, in this case, it actually thought we wanted to convert that one into a string, but and made an array of strings. But you can also have, what's that?
Didn't you say earlier you were not allowed to put different data types?
What you can't do is put a data type into an array that isn't ready for that data type. But if you initialize an array with multiple data types, it can handle that. So essentially, the way it works is that when you create an array, it needs to know what kind of data it's going to be storing. And so if you create an array like we did like here, well, not there, but like we did earlier for our array U, all we gave it was integers. And so it created an integer array. And so we can't put anything but an integer into it. But here, it basically decided that we were trying to create an array of strings, and that's fine. I believe if I gave it something like an object here, it creates an array whose data type is object. And then you can put whatever you want in it. Now that said, if you have an array that's storing objects, the memory efficiency of that array is going to be very low because the reason arrays are very performant is because they can store things like integers in very, very simple representations in memory that you can't do for normal Python objects. If you want to know more about that, I can talk ad nauseum after the lecture about it. But there's a lot of details about how things get stored in memory that go into why you can only efficiently store numbers and not things like objects in an array that way. Okay, so I just mentioned this D type being object. Let's talk a little about that. So for our array U, which we made using integers, we can ask for its D type just like we did the shape. And it's going to say, look, a D type of int64. So D type stands for data type. And it's the type of the cells of the array, basically. Int64 means integer, and specifically a 64-bit integer. So just to explain this very briefly, when we store numbers in memory, we store them in binary with ones and zeros, and each one or zero is a bit. And so if you have just one bit, you can store a 0 or a 1. If you've got 2 bits, you can store a 0, 1, 2, or 3 by just putting those numbers representation into binary. For numbers that we store in computers, we almost always store them in as 8-bit numbers, which are bytes, as 16-bit numbers, which are honestly kind of rare these days, 32-bit numbers, or 64-bit numbers. And basically, the higher the number of bits, the higher the values, and the lower the values you can store. So 64-bit numbers, I don't even remember the range of 64-bit numbers. It's enormous. I've never needed a number that you couldn't store in a 64-bit number. 32-bit numbers go up to about 2.5 billion or something like that, and down to about negative 2.5 billion. So that gives you a sense of how big they are. 64-bit integers are exponentially larger, so they can store really big numbers. When we create an object, so suppose we're creating an array and we're giving it a list of integers like we did earlier, but we don't want it to represent them as integers. We want it to represent them as floating point numbers. In that case, we can pass a D-type argument and say, basically, we want this to be a floating point number. And if we do that, you notice that it gives us back floating point numbers as the cells in the array. Now, float here means whatever size of floating point number is most natural for your computer or whatever your compute environment is. Most of us these days have 64-bit computers, The Jupyter Hub is definitely a 64-bit computer. So if we capture this array as A and then print out A.D type, it's going to say float 64 because it assumes that if we just say float, we want a float 64-bit floating point number. If we wanted a smaller floating point number, we can say, hey, NumPy, we want to use the float 32 type. And then our D type will be 32-bit. Now, when would you actually want to do this? Well, how many of you have worked with fMRI images before? Okay, so how many of you have worked with an fMRI image that was too big to fit in memory? Yeah, okay, so that's some of you very enthusiastically. Yeah, okay. So if sometimes, and the reason fMRI images are often too big to fit in memory is because they have 4 dimensions. So if you've got something even, let's just spec this out. Suppose you have something like a 1 millimeter size voxel, and you've got 200, let's just say 200 by 200 by 200 voxels in your image. And then you're taking, and then this scan goes for 5 minutes and has a 1 second TR. You're going to have 600 frames of these 200 by 200 by 200 voxel images. That's a lot of numbers to store in memory. And if each of these takes 8 bytes, which is the size of a 64-bit floating point number, that's the number of bytes of memory you have. And if I were to convert this into gigabytes, just bear with me here. So that's about almost 36 gigabytes of memory just for that one fMRI scan. And if instead you store it as 32-bit numbers, which just take 4 bytes, you can store it in half as much memory. 17 gigabytes is much more likely to fit in memory than 36 gigabytes. Depending on how fine your resolution is, this may or may not help, but this is the kind of thing that might matter sometimes. So if you're okay losing a little bit of precision, you can always go to a lower data type. Okay, any questions on any of this so far? I just want to make sure I'm not running too fast here. Okay. In addition to the floating point type, I'm just going to make some quick arrays here. You can have D type of int for integer, or you can use np.int32, for example. There's also a type for what's called an unsigned integer. If I make a uint32 for an unsigned integer, then you can't store negative numbers in that array, but you can store positive numbers that are twice as big. So in an int32 array, you can only store a positive number up to about 2 billion. But in an unsigned int32, you can store a positive number up to about 4 billion. That's the difference there. You can also have a complex number. And that will convert whatever your input is into a complex number. Works fine. Okay.
Array, what's number 0? What are you mean by this here?
I'm making an array with just one number in it with no dimensions. Yeah. So this is a 0-dimensional array. Yeah. Yeah. Or we could make a 1-element vector, for example. Yeah. Okay. I'm just going to briefly mention this other function called np.asArray. So the np.array function always gives you a new array back. If you pass it an array that already exists, it will make a copy of it and give you the copy. If a lot of times when you write a function, you want the input, whatever argument the user passes in, to be an array, but you're not sure if they're passing you an array or a list of numbers, and you need to make sure it's an array. So oftentimes, let me give an example here. So we have some argument that's like, keep that the way when we've been using it. We've got some argument that is being passed into our function, and we want to say, we want to make sure it's an array. But if it's already an array, we don't want to copy it, especially if it's a great big like fMRI array. We don't want to copy that array. We want to just use the array they gave us. You can say as array, and it will make sure that whatever it returns is an array. So here, it actually gave us a new array by copying this data. But now, if we say np.asArray arg, so we turned the argument into an array here, and now it's going to give us back the same thing, but in fact, it's just giving us back arg. It's not making a copy, and we can check that by asking, is arg the same object as np.asArray arg? And it will say true. On the other hand, if we say np.array arg is arg, it's going to say false because this function makes a copy of arg and gives us back the copy. Real quick, is anyone not familiar with the is operator versus like equal equal? Okay. Yeah, so equal equal is slightly different. So equal equal will check if two things are equal. Is checks if they're literally the same object. Yeah, so two arrays can be equal without being the same, if they're just copies of each other in memory. Now that said, since we're talking about equal equal and operators, let's talk about how arrays handle operators. And this is really where a lot of the magic of NumPy kind of happens, I think. Let's take our array M, or our matrix M that we made earlier. And I'm just going to say, whoops. I'm just going to say M equal equal M. So one might hypothesize that this ought to return true, but it's not going to do that. It's going to do something a little different. When we give an array an operator like equal equal or plus or greater than or times, any of those, it's going to try to run that over every element in the array instead of over the whole array. So what it did here was it said, hey, is the first element in the first row of M equal to the first element in the first row of M? If so, it gives us a true. On the other hand, if we said something like M times 2 over here, we're going to get false for almost everything except for this element because that element's a 0 and 0 times 2 is equal to 0. So that's fine. And you notice here I use the multiplication operator. So if we just see what that did, if we just say M times 2, it just doubles every element of the matrix. So operators like times and addition and greater than and less than and equal and all those, they all will thread across all of the elements of the array. Okay, what if we have something like M plus, and then we give it a list or another array. So let's suppose I want to say M plus 1 comma 2. So there's a few possible outcomes here. And I'm curious what people think is going to happen. One possibility is that it's going to add 1 comma 2 to every row. And that should work. One possibility is that it's going to try to add 1 comma 2 to every column, and it's going to fail because there's not a correct match of size. Another is that it's going to try to add 1, 2 to every element and maybe make this a 3D array. Anyone want to take a guess? That's right. It's going to add them to the row. So if we run this, it's going to add 1, 2. Oh, right. Let's print the matrix for reference here. Okay. So it added 1 to this first column and 2 to the second column. Same here, and same with this bottom.
Which is X to every
It added this row to each of these rows. Yeah. So if we do something like M plus 1, 2, 3, now you might think that it would add to every column because there's three rows, and so every column could fit, but that's a little too willy-nilly. It's going to actually say, I don't know how to do this because you have your rows have 2 elements each. And you've given me 3 elements, and I can't add 3 elements and 2 elements. Does that make sense why we got this error? Okay. There's actually a lot to be said about how NumPy does this. This is a topic called broadcasting. So arrays will try to broadcast their inputs. And the basic idea here is that if you have an array and something else that you're trying to do like a binary operation with like this, if the shapes of the two things are the same, it's just going to go element by element and do the operation. So if m plus m, no problem. It just does each paired element and adds them. If they're not the same, if one of them has fewer dimensions, it's going to try to run the operation over every row. And if, for example, we had a 3D matrix, it would try to go over every, it would go over every row, and then it would take the sub-element and go over the first dimension of that, and it would basically try to push the operation down to the very last dimension of the array as much as it can. If we wanted to add something to every row here, so we wanted to add, we wanted to do this operation such that we got 2 to 2.75 here, because we added 1, 2, and 3, then we need to do something slightly different. We would need to instead give it a column vector. So we could say 1, 2, 3. Now, I'm just going to copy this and point out that if we turn this into an array, we get a column vector. And basically, because this array now has the same number of dimensions as m. This isn't actually an array, but it'll turn it into an array as soon as we run the operation. And it's going to say, oh, look, you've got only one column, but I have 2 columns. But that's okay. If you've got 1 and some other number, I'll broadcast the 1 across all of the columns. So this will actually work just fine. 2, 2, 2.75. Let's print m for reference. So it adds 1, adds 2, and adds 3. Okay. Does that make sense to everyone why that worked? Okay. Again, the name for this is broadcasting. I guarantee that at some point you're going to have to look up broadcasting and figure out why your arrays aren't adding correctly. There's a lot of nuance to how NumPy allows you to broadcast. This is the very basic kind of idea.
Not every row, but like specific rows, or
Yeah.
how would you combine those?
Okay, great question. If you wanted to do operations on just some rows, so for example, you sort of anticipated one of my examples later. So for example, let's suppose we have a matrix of 3D data points. So let's say points equals, and I'm going to use a function we haven't seen yet, np.random.randn. This is a function that draws random numbers from a normal distribution. And we can give it a number of rows and a number of columns and whatever dimensions we want. If we want a 3D matrix, we can say 10 by 3 by 5 or something like that. But we just want a matrix of points, of 3D points. So we're going to ask for 10 rows and 3 columns where the columns are x, y, and z. And I'll just print that out. So it gives us back this matrix. Now, suppose that we wanted to, for example, and I'm just making this up, but we wanted to say everywhere that the x coordinate is less than 0, we want to set the z coordinate to be equal to 0 for some reason. I don't know why, but for some reason we want to do this. Okay, so if x less than 0, set z to 0. So what we can do is we can say, I should say, points. Okay, so we have this points matrix. If we want to just extract the x data, that's just the first column. So we're going to say all rows, column 0. And if we want to know if it's less than 0, we just say, is it less than 0? And I'll just run that, and you can see that it's like false, true, true, false, etc. So it's telling us where they're less than 0. So I'm going to save this as a variable called ii. II is commonly used to stand for an index variable. I'm not sure why II became the variable, but people often use it to mean an index variable of some kind. And then if I ask for points II, 0, it's going to look at this binary, it's going to look at this index, which is basically a binary mask of which elements we care about. and it's just going to take the subsets of that column that go with those points. So in our case, we had what, 5 elements that were less than 0 here. 1, 2, 3, 4, 5. So it's printing them out 1, 2, 3, 4, 5, and you can see that they match these elements here. If we wanted all of those columns, we could request all those columns, and it'll print out just the columns with x less than 0. And now, if we wanted to, I'll just have that print that. If we wanted to set the z value to be equal to 0, we could say points of ii, and then our z column is column 2 because it's the third column, and we can just say equal 0. And just like with plus and greater than and less than and all those, when you set an array like this equal to something, it will try to broadcast over the array as well. So it's going to go over each of the elements we specified here and set them equal to 0. And then I'll just have points at the end. So here it printed out points because I had a print statement here. But then at the end, this is what it produced. And you can see we've got zeros everywhere that the x is less than 0. Yeah, great question. Any other questions so far?
Since that's negative.
What's that?
It also prints them as positive.
Right. So at the end, we just had it print out the whole matrix. And also your matrix will be different than mine because we randomly generated these matrices. So for me, I had 5 points that were negative, but you might have had a different number. Okay. Oh, wow. Okay. So I'm gonna mention just a few more things about NumPy, and then we'll move on to pandas. So first of all, there's we just talked about the random.random function for making random arrays of particular size with the random numbers. There's a few other kind of handy array creation functions. So for example, if you want a range of numbers like 0, 1, 2, 3, 4, etc., you can say np.arange, and this is just like the range function, but it gives you back an array instead of a range. So if we say arange 10, it'll give us back 0 through 9. Another really handy one, and this will be familiar to all the MATLAB people, is linspace. So if we want like 6 numbers starting with the number 1 and ending with the number, starting with the number 0 and ending with the number 1, that are evenly spaced, we can say, I want to go from 0 to 1, and I want 6 numbers, and it'll give us back that range of numbers. One more that's pretty handy is you can say np.full, and then you can say, like, for example, I want a 10 by 3 matrix. We just give it the shape first, so 10 rows and 3 columns, and I want this to contain the number 2.5, and it fills that array with that number. Okay. The other really important thing that is NumPy contains are just all of the basic math functions you'd ever want. So if you've used Python's math library, the math library, honestly, almost nobody uses this library, but you can import math, and then there's like math.log, for example. That's a function, and it works, but it only works on individual numbers. You can't pass an array to math.log. If you do that, it's gonna say, I don't know what this is. I only work with scalars. NumPy also has a log function, and it will work with numbers just fine, but it will also work with arrays, and it will broadcast along the arrays just like the operators do. So if you ask for the log of our vector u, it gives us back the log of every element. I won't belabor all the functions that NumPy has, but there's tons and tons, things like log and exponential and sine and cosine and arctangent, and there's also accumulation functions like the sum or the mean or the standard deviation. So if you want to know the standard deviation of our vector, that's the std function. There's mean, median, percentile, tons and tons of functions. And all of them work really nicely over arrays or array-like inputs. So you can also just give these functions a list and it will treat them like an array and work just fine. Okay. We haven't gotten through quite everything I wanted to talk about in NumPy. There's a little more in the tutorial notebook, but I want to pause here and ask it for any questions. And then we'll kind of move on and pretty quickly get to pandas here. Okay. The last thing I want to do before we go to pandas is just talk really briefly about visualizing arrays. And I will mention that I don't think we have time to go over it right now, but in the notebook, the intro to NumPy notebook is a section on vectorized programming. And this is kind of the concept that if you write something with a loop in Python, it's going to be slow. Python's loops are very slow, and that's just how Python is. But if you can do that operation using NumPy as a vector, for example, by saying, oh, is u greater than 5? Can we set the elements where u greater than 5 is equal to 0? Like that kind of thing. That's sort of like doing a loop. Like we're going over every element of u and asking if it's greater than 5 and then setting it to some value if it is. That will run really fast. It will run like 100 times faster than if you write the loop yourself. And that's because NumPy is written in a really low-level language. It's written in C. Python is a really high-level language that does a lot of extra work for simple things like loops. Anyway, I'm happy to talk about this more later or in a review session next week or something like that. But there's some information about that in the tutorial as well, and it's kind of an important topic. Okay, so I just want to talk about the matplotlib imshow function real quick, and we'll come back to that bit of data that we downloaded. So I'm going to go ahead and import matplotlib.pyplot as PLT. Matplotlib is the plotting library for the scientific plotting library for Python that's based on the interface for MATLAB. It was inspired by the interface for MATLAB, and so we'll be using that to do just a little bit of plotting here. And recall that earlier we grabbed the array out of the nifty image that we were looking at. And what I want to do is just plot a slice out of that nifty image and make sure that we actually got a T1 weighted image. So to do that, there's a function that's pretty much just for this called imshow. If you're familiar with MATLAB, you probably know this function. Basically, you can give it a 2D image array, whether it's an RGB image or it's just a matrix of numbers, and it will make an image of them. So I'm going to give it the 100th row of our array, and I'm going to add another argument, cmap equals hot. Cmap is for color map, and there's a kind of like a cold hot color map. If we run that, it should give us a nice image of this person's brain. And if you want, we could say, instead of getting the 100th row, let's get the 100th column. That'll just give us a different view of the brain. And I think if we ask for something like the 120th slice, we get a pretty nice, yeah. So for example, you mean like, yeah, so if you ask for array 100, it's the same as if we asked for this. Yeah, yeah. I think here I've got 150, yeah. Okay, so I use imshow all the time, especially with MRI data. This is kind of some of the basic tools for looking at these kinds of data. Okay, before we go on to pandas, any questions or any burning topics that I didn't address that you'd like to hear about? Yeah, sorry. All right. So let's switch gears a little and talk about pandas. Unfortunately, I don't think we're going to get through nearly everything that I put in my notebook for pandas, but we'll at least talk about some of the basics. How many of you have never used pandas before? Okay, so a few people, yeah. So how many of you have used R before? Okay, so Pandas is Python's attempt to make as nice an interface for tabular data as ours had. And it is just an attempt. I don't think it's nearly as good, but it is the best we've got in Python. And honestly, it is pretty good. It's just R was built around this, and so R is very good at this kind of data. Um, so since we're a little low on time, I'm actually not going to live code this next part because we're going to start by reading in some data from the NSD again. That's a data frame or a Pandas tabular data. What I'm going to do here is I'm going to open the intro to Pandas notebook in this directory, and I'm just going to scroll down to this cell right here. I'm just going to copy the whole cell. I'm going to encourage you to do the same thing just to save time. So again, over on the left, go to the intro to Pandas notebook, and it's the second code cell after the import statements. Yeah, we'll do that. Yeah, don't worry. Okay, so coming back over here, we're going to start by importing Pandas. And people often import Pandas as PD. That's just, again, just the convention people use. And then I'm going to paste that cell. And you notice that once again, we're telling this to use the cloud path lib to create an S3 path to our NSD root. Actually, we can just delete all this because we already did that part. You can start with this behave dir path equals NSD root slash et cetera, et cetera. And basically what this is going to do is it's going to go up and it's going to download for the NSD experiments, they had like a one or a, I forget, an n-back memory task basically that the subjects were doing in the scanner. And what they did was they saved the results of that behavioral task as essentially a spreadsheet. And spreadsheets are really what Pandas is all about, tabular data spreadsheets. So this code should read this in. It will take a second, but not very long. And what comes back is this, I'm going to make this disappear so it's easier to see, is something that looks kind of like a spreadsheet that you can kind of browse as if it were a spreadsheet. You notice it has a column for subject, for session, for the run, and for the trial, as well as a bunch of other stuff we'll talk about in a minute. I honestly don't know what all of these columns are for. I know that what some of them are for. We're just going to worry about the reaction time that subjects had and sort of information about what run and trial and stuff that they were working on. Okay, so before I go on, is anyone unfamiliar with this kind of data, like tabular data that's organized in rows and columns like this? Okay, yeah, this is like Excel is the classic tabular data browser. And lots of scientific data is best stored as tabular data, and there are some nice, convenient things about analyzing it that we'll kind of go over here. So what we printed out at the end is this behavior data, that we read in using the read CSV, the pandas.read CSV file. CSV stands for comma separated value. And if you're not storing tabular data in an Excel spreadsheet, you're probably storing it in a comma separated value file where every row of your file has commas that separate the different cells. And then the next row is the next row of the spreadsheet. So Pandas will read these in and turn them into these objects called data frames. And if we ask for the type of this behave data, we'll see that it's a Pandas data frame object. So Pandas data frames store tabular data. Okay, so just some simple operations that we can do. First of all, we can pull out a column. So if we say behave data and we ask for RT, RT is reaction time in this data frame. And I got that because if you scroll over, you'll notice there's a column named RT for reaction time. So this is, I believe, the reaction time in milliseconds for every trial that the subject participated in. Now, if I don't think we're going to have time to get through this story, but if you look at the intro to Pandas notebook, I kind of talk about maybe we could have a hypothesis that the longer the subjects are doing this experiment, the better they get and the faster their reaction times. And if you go through the notebook later, I kind of walk through that and then at the end plot some data essentially determined that that's not true. Subjects actually get slower as they go for some reason, but I don't have an explanation for that. That's just what the data say. Regardless, we'll just look at, well, we're mostly going to look at this reaction time as kind of an example of data in the tabular data. Okay, so we can pull out the reaction time or some, really any column we can just ask for as a string like this. We can ask for the session. Now, and it gives us back something that's kind of like an array, but not exactly an array. Pandas uses NumPy under the hood for everything. So deep down in your Pandas data frame are NumPy arrays. Now you don't see them because Pandas has wrapped those NumPy arrays in different types that have different capabilities. But fundamentally, most things that work on NumPy arrays will work in some form on a Pandas data frame or a Pandas column like this. Pandas calls these series objects. It's got a little bit different nomenclature for things. So for example, if we wanted to pull out just the rows where the session is equal to 1, we can say behave data, session equal to 1. Now this is we'll go ahead and run this just to show that it works, and I'll scroll up so you can see that code. So there's something a little bit weird about the syntax. Now this part in here, this is straightforward enough. This is basically, we want to broadcast this equality operator over the columns of the session, or the rows of the session column. And this by itself, whoops, if we just run it alone, will give us back trues and falses just like NumPy would. Now, we can also pass those trues and falses just like we did with NumPy as a mask, as a Boolean mask, and it will give us back just the rows where session is equal to 1. And you can kind of tell that works because these are all 1s and we don't have 40s at the bottom anymore. Now, what's a little weird about this is that in NumPy, if you pass session right here, that's like a column index, not a row index. So you can see that Pandas treats its indexing a little bit differently than NumPy. Basically, if you pass a string, it's going to assume you want a column, or you could pass a list of strings. Whoops. So if we said behave data, and then we gave it session and reaction time, it'll give us back just a data frame with those 2 columns. However, we also see up here that if we give it a Boolean mask, it's going to work on the rows. And those are basically the 2 ways that you should be using this basic indexing operator. If you just ask a data frame for a Boolean mask or columns, that works fine. If you want to do something fancier, there are a couple different ways to do it. So if, for example, we wanted to extract the 3rd row in the data frame, whatever it is, we would say behave data.iloc for index location. And we would ask for row 2 because that's the 3rd row. And it gives us back, I mean, this is the data from row 2. It's in a kind of weird print format here, but it is that all the columns of row 2 that it gives us back. Or we could say, we want columns 2 through 5, rows 2 through 5, and it gives us back those rows. Similarly, we could ask for our columns by index here too. So for example, if we just wanted the first 3 columns, we could put :3, and it would just give us subject session. Okay, so a data frame.iloc basically is indexed just the way a NumPy array is indexed. On the other hand, there's also behave data.loc. Loc, instead of using indices, uses it uses the data frames indices. So for the columns, let's just think about columns first. That means actual column names. So if we ask for session, all the rows, we ask for behave data.loc for all rows and the session column, it'll give us back just that one column. Or we could ask for session and reaction time here, and it'll give us back that data frame. Now, you notice that this one column over here doesn't have a title. It doesn't have a header here, and it's in bold. And that's because this is the index column of this of the rows of this data frame. Now, in some cases, in this case, the index is just 0, 1, 2, 3, et cetera, et cetera. So it's basically this is indexed just like it were a NumPy array. But sometimes, so let's just look at behave data again. Sometimes you notice this has subject, session, run, trial. These are really all columns that tell us what are the measurements that come after this, right? These are sort of indices as to what we're looking at, and then these are data about that particular trial, right? So there's sort of a divider here that's not explicit, but just a divider here where these 4 columns are telling us what we're looking at, and the rest of these are telling us the data about that measurement. So we conceptually might want to index by things like subject and session and run and trial, rather than by 0, 1, 2, 3, 4, et cetera. And so in a lot of data frames, you'll end up with one or more columns that act as an index themselves. And in that case, when you run loc, you can provide those values here. So let's just look at an example. Now, what I'm going to do is, first I'm going to pull out just, to keep this simple, I'm going to pull out just the first session and the first run. So let's get subdata equals behave data. And we're going to say, first of all, we just want data where the session is equal to 1. And you notice I put this in parentheses because I'm going to add another condition here, and I'm going to separate them by a pipe, the vertical line operator. That vertical line is a union operator, so it's going to go item by item, and it's going to say true and true, or true. True. We're going to call this or. True or true is true. True or false is true. False or true is true. False or false is false. So it's going to go element by element and say is either of these true. Actually, what I meant to put here is an ampersand, and because we want both of these to be true, and we're going to say behave data run equals 1. So we're going to pull out just the rows where the session is 1 and the run is 1. I'm going to say subdata, and we'll just print that out. And you notice that if I scroll the way down, we seem to have only run in session 1, but we have a bunch of different trials. So just to demonstrate this, this indexing, we can say subdata equals subdata.set index to trial. And then you notice that we have this little, this trial over here, and the trials are in bold. Now, really all we did here, these trials start with 1 instead of 0. So now, if we ask for subdata.loc of trial of 1, we're going to get, oh, you know what? This is trial 1. You just have to believe me. Sorry. Let's say 1 through 3. Okay, we're going to get trials 1 through 3. Whereas if we had done iloc, we would have gotten trials 2 and 3, because it's going to look for the index, not the trial number. So for a lot of, in my experience, for a lot of data frames, the rows are just indexed like this. So most of the time when you use loc, that first spot, that first argument here, most of the time when you use loc, that first argument is going to be the same as if it were just a matrix. But sometimes you'll have data frames that are indexed according to some particular value. And in that case, you can use loc to look at those values. Okay. Okay, any questions on any of this so far? Okay. So let's see, what's the best way for us to spend the rest of the time here? So let's, yeah. Okay, let's think about some other kinds of operations we can do with pandas. Let's start by selecting a subset of our data, the behavior data. And we're going to select specifically just some of the columns. We're going to select the subject, the session, the run, the reaction time, and whether or not they got the trial correct, the is correct column. So if we just select this, we'll get a sort of mini data frame with just the columns we care about here. And I'll keep that up here for now. Now, something that you often want to do in Pandas, or at least that I end up doing pretty often, is I want to select some of the data and then I want to run a correlation over like the columns against each other. And Pandas has a bunch of built-in functions that do exactly these kinds of operations. We aren't going to have time to go over nearly all of them. I don't really know all of them, to be honest, but this is just an example, and you can Pandas has a great documentation and has good tutorials for all of this kind of stuff. So if you find yourself needing a function kind of like this, there's a good chance it exists and you can go find it. But I'll just say, okay, let's take data. We're just going to run data.core for correlation. And what it returns is a matrix of just a data frame where the rows and columns are both named the same things, because what we did was we took all the columns of this data frame and correlated them with each other or with themselves. So we took session versus or subject versus correlated to subject, subject correlated to session, etc. And that's what we have here. So NaN stands for not a number. Basically, it's saying, honestly, I'm not sure why that came up, NaN. Since these are all ones, it probably should have said one, but I'm guessing there's a missing value somewhere in this column, and that's why it came up with that. Yeah, so for session, it said, yeah, I bet these are strings. I bet the subject is a string, and so it said, I don't know how to correlate strings together. The session, on the other hand, is an integer, so when you correlate a bunch of ones with a bunch of ones, you get a correlation of one. That's session by session. What we really care about is something like, what's the correlation between their reaction time and the fraction they got correct? And that's over here. That's the reaction time and is correct, and it's, a little bit negative. This is a good example of where the loc is different than the iloc, though. So let's capture this. I'm going to say r equals data.core. And then if we wanted to pull out the correlation of the reaction time and is correct, we could say r.iloc of 0, 1, 2, 3, and 4, because that's the reaction time in the is correct columns. But it's a lot easier to say, hey, I want to know how reaction time correlates with is correct. That makes sense? So this highlights the fact that because this little data frame is indexed by column names and also by row names instead of row numbers, when we use the .loc, we have to give it the indices that go with those axes. So we have to give it the name of the column and the name of the row. Okay. Any questions on this? All right. Okay, let's talk a little bit about grouping operations. So a lot of times, this data set is actually a great example because we've got multiple runs. And we may want to calculate the average reaction time per run and see if that reaction time is decreasing as you go to higher runs to see if the subject's getting faster. So we can do that with a function called group by. So again, I'm going to go back to behave data. And I'm going to say group by. And we're just going to group by the run. And you can actually pass a list of columns here. So for example, if we had all of the subjects in one data frame, we could say group by subject run. Or here we could even group by session run, since there's both sessions and runs in this table. But for now, we'll just worry about run and keep it simple. I'm going to call this groups equals behave data.group by. I'm going to just print it out so we can see what it is. And it's a particular object that represents group by, so it doesn't tell us a whole lot. But there's some pretty basic operations that we can do that are pretty straightforward with groups. So what this has done is it's gone through and it's separated everything out to run equal 1, run equal 2, run equal 3 into separate like data frames, basically. And if we just say groups.mean, it's going to give us back the means of every column for each group. So that may not be immediately obvious, but remember we grouped by one, or excuse me, run. And so what it's telling us is, oh, you grouped by run, so I'm going to index this data frame by run, because that's how we uniquely identify the different groups. And then it just takes the average of everything where run is 1. These are the averages. So we can see the reaction time for run equals 1 is here, run equals 2, run equals 3, etc. Yeah.
Is there a convention for which functions are NumPy or pandas are like all lowercase or caravan case, or do you just have to memorize it?
Yeah, so is there, the question for those online is there a convention for camel case or snake case, or the various case ways of doing like uppercase and lowercase in function names? So NumPy and pandas mostly, but not entirely, follow the typical Python convention, which is types are camel case. They start with a capital letter. So for example, data frame is a type, and so it's in camel case. Normal functions like pd.read CSV are usually all lowercase, separated by underscores, although a lot of Python programmers just drop the underscores, and so you end up with things like as array and not as underscore array. I would say this is a loose Python standard or Python convention, but functions are typically in lowercase only. Now, I said that it was mostly this way, and a great example of a violation of this is that the type of a NumPy array is ND array, stands for n-dimensional array, but it's not camel case. And I think that's because the people who wrote NumPy felt that this was a fundamental enough library that they didn't have to capitalize their types. I really don't know, but that's the case anyway. Okay, other questions? Okay, something else we can do with this group bias, aside from calculating things like the mean and the standard deviation of the columns, we can just iterate through it. So we can say for the run ID, comma, the group in groups, and the groups object that we created, I'll just remind you, it was up here where we ran this group by. I'll copy that down here. This groups object, excuse me, this groups object can be iterated over, and we'll just go ahead and print run ID. Mean RT, mean reaction time is equal to, and then we're just going to run np.mean on group RT. So our group is basically just a data frame. This group object here is just a data frame for the elements where the run is equal to 1. And so when we run this, it's going to iterate over all of the groups, 1, 2, 3, 4, 5, etc., up through run 12, and print out the mean data for, reaction time for each. Okay. Any questions? All right, so we're almost at the end of time here. Again, there's quite a bit more content in the notebook that's attached. I thought we would have a lot of extra time, but apparently I was wrong. Is there, rather than start the next section, I'll just kind of open it up. Is there anything about any of these libraries or about other libraries that we didn't get to that people would like to hear about in the last few minutes? Yeah.
General question. Organizing data between pandas and NumPy. Like sometimes, for example, if you have like an array of data for each subject and you want to have like an issue that I sometimes run in code is that like I have a bunch of like metadata of like this is the subject ID, this is the run number, this is the particular task they're doing, and then I have an array of like, oh, these are all the values that they generate.
Yeah.
What's like the best way of like linking between the two or like storing them all together so that I can like do all these fun things like
Yeah.
slicing.
Okay, that's a great question, and I think it's kind of a perfect question for the amount of minutes we have left. So, okay, so the idea here is you've got some subject and you've got metadata about that subject, and maybe it's not necessarily a subject. Maybe this is like a measurement, and so this is going to be subject 1 and session 12 or something like that. Let's keep it simple, and that'll be all our metadata for now. Okay, and then we've also got measurement results, and it's an array of reaction times or something. I don't know, and so it's going to be whatever. Just put some numbers in there. So we've got some array of actual numerical results from the measurement, and then we've got metadata about the measurement. And the question is kind of how do we take this and organize it into something that we can use with pandas or NumPy or whatever would be most natural. So for this kind of example, what I would say we really want is a data frame with 3 columns. They're going to be subject, session, and measurement. So there's a little bit more information about how to create pandas data frames in the accompanying notebook, but as a quick example, you can create a data frame from a few things. One is a dictionary of columns, and another is a list of rows. And the ways you do that, so for this particular set of data, we need to either produce something that looks like this. Oops. Because our subject is 1 for all 3 of these measurements, right? And then our session is 12 for all 3 of the measurements. And then our measurement is just going to be this array. And so this is one way we can do it. If we say, hey, pandas, give me a data frame, and I will capture that there. If I say, hey, pandas, give us a data frame of that data, it can do that just fine because we have 3 rows for each of these, and it can match them all up with rows and columns. The other way we do that is to say, instead, I've got a list of the rows, and in that case, we need to give it a bunch of dictionaries. Now, this is going to be much more verbose. So that would be our first row. And then to save some time, I'm going to copy and paste a couple times because these are the same. We just have different measurement results for each one. Whoops. And then if we ask pandas for a data frame, it'll give us back the same thing. Now, these are 2 ways you can initialize a data frame if you don't have the data already in comma separated value or anything like that. And I think that the kind of important observation here is that the way that we organize tabular data is usually to duplicate a lot of column data. So the way we have everything represented here, we've just got one dictionary of the metadata, and it goes with all these measurements. But if we're going to put that into a tabular data frame, we're going to have every row, 1 for every measurement, but we're going to duplicate the subject and the session for all those rows. And that's it feels a little wasteful if you're used to programming in a language or in a paradigm where you're trying to save memory at every step, or like where memory is really scarce. In particular, you would never take you'd never take an MR image and put all the voxels into a data frame where you had row, column, slice, and value, because that would be a really inefficient way to store a NumPy array. But for a lot of data, like all of the experimental data for all of the sessions for this subject in the NSD is only like a few kilobytes worth of actual data in CSV format. And having it in a data frame makes it very easy to query and extract subsets of the data and that kind of thing. So that's why we kind of organize things this way in tabular data. Okay, it is now noon. If you want to know the answer to the question of whether or not subjects get better or faster at the experiments as they go, you have to go look at the accompanying notebook. I'll say that the very last thing in the accompanying notebook is an example of using the library Seaborn, which is kind of made for plotting these kinds of tabular data. And so with just like a little bit of code, you can take this whole data frame and plot all the stuff we would need to look at that. But we're out of time, so if you want to look at that later, feel free to send me any questions or anything. And yeah, that's it for now. So we'll see you after lunch. All right, bye, online people. We'll see you after lunch.